Okay, great. So it's our second last speaker for this term. Great pleasure to introduce Peter, who's going to tell us about his work on, I think, inspired with the forecast of like 10,000 years of data. I think that I like the top title even better because you called it about parallel universes, parallel processing. Thanks. So anyway, thanks, Peter. We look forward to your talk.
Thank you, Kesha. I can see from Maddie's reaction she hasn't heard this yet. Some people have in the symposium, so I've been. But I'll go in this talk into more depth underneath the whole problem and why is this principle useful and important in trying to bring forward energy systems, but specific electricity systems that are carbon-free. Right. So let's go start with an example of a weather situation that is of particular interest to electricity system. So throughout the whole PhD, I've been looking at electricity system over Europe because I'm from Europe, so I'm the most familiar with it. But these principles should be applied in all larger scale systems, anything that's bigger than, let's say, like anything that you need to care about spatial differences in weather, right? So here is one particular example of a weather situation that's interesting. So this is a record of weather from, I'll pause it, from last year. It's roughly the same time as now. At the bottom, it's you can see it's like June, end of June 2022, and it starts in the night. And you can see this is a satellite view over which the kind of animation of wind has been overlaid. And these are the two most important factors for generating electricity, right? Solar and wind turbines, they depend on illumination from the sun, which is both blocked by the shadow and also by clouds. And then renewable systems with offshore and onshore wind turbines depend on wind speed. They don't particularly usually care about wind direction that much. And you can see these are three, this is from a satellite, Meteosat, I think, that in 3 hour chunks shows you a progress of a certain weather situation. So in Europe, most of the time, there is a wind blowing from the west. This is to do with the larger cells of circulation over Earth and the fact that we're in this kind of mid-latitude. And so you can see in these 3 hour chunks, there's what's called a front that's coming from the west over Europe. And as the sun comes in, so this is 7 a.m., this is 3 hours later, 3 hours later, midday, 4 p.m., and then this is 7 p.m., which you can see that this big front is pushed over to Germany, and this precipitated a lot of the moisture in the air into the clouds. And suddenly you got this large cloud over Germany that's covering most of the western part of it. And in this situation, there is almost no solar generation power. It's a fraction of what you could do with any installation. You can also see, because the front kind of collided with the western winds, that the winds are kind of pushing against each other. And then here, right here, there's almost no wind whatsoever. And this is also at 7 p.m., where usually people come home from work, and there is in the classical electricity system, there is the highest peak of demand of electricity at roughly this time, and a little bit later when the sun disappears. And so the question is, what would you do in this case if you want to supply this large population? This is so this place is one of the most populated. There's what's called in sociology the blue banana, which is just it's an agglomeration of population between London and Milan, and this whole cone, Frankfurt, Stuttgart, there's a lot of population, a lot of electricity demand. And so what would you do? Typically is German electricity system has a lot of backup coal, and at this point the coal plants would go on to supply electricity to the system, right? Coal is one of the dirtiest sources of electricity in terms of carbon release, because simply there's just more carbon per electricity bond for the energy in coal. And yeah, so this is if you move into a future where you no longer have electricity system that depend on carbon energy, carbon releasing energy, you need to solve this problem, right? And so there's only so many solutions. Yes, this video. There's only so many solutions that you can do, right? So one thing that you could do is use a carbon-free, controllable, pilotable source of energy. I'm not quite sure pilotable is a common word in English, but in French, the French have amazing, two amazing words. Pilotable is the thing that you can control. This is the traditional paradigm where you spin a turbine based on what the demand is. And then they have, for the other English use variable, uncertain, the French word fatal. You only depend on fate, right? It's this lovely word. And so if you have pilotable sources of energy, you can just ramp up the demand based on, you can also use the meteorological predictions to predict a little bit ahead, but usually the systems can be flexible enough to supply as much as you need. And the one main, you could have some carbon capture. None of this seems to be plausible in the future to do in any economic scale. So the one source is nuclear, which is not as controllable as some other ones, but is, if you know that well ahead that something like this can happen, the nuclear power will be there. Other one is just storing it in batteries. Been a lot of development recently. And this probably will be the solution to shifting the kind of peak of solar into a few hours later into the peak of demand. But those costs, and the more energy you need to store, the more they cost. And if you ever endeavor to store something for the next day, then you need to dedicate that much more storage and that much more cost. You can overbuild capacity. So you've got this classic notion that the levelized cost of electricity for wind and solar has dropped significantly over the last years, but levelized is a very strange concept once you get into large proportion of renewables, because maybe if the cloud reduces your solar to 10%, you could use those cheap solar panels and build 10 times many, but suddenly the cost also goes by a factor of 10. And most of the time you're generating electricity which you don't need. And you could use demand control, right? So we used this notion where you plug a charger into the wall, it will start charging exactly as much you do. If you turn on the kettle, it will start heating up. And these are massive swings of demand, right? Not so much the charger, but if anybody can choose at their own will to just draw power from the demand without any pre-negotiation, that's just something that's the nature of the current system. And this is kind of miraculous. This is always dependent on some inertia in the system, on the way that the system was generalized, where the feedback would be feeding directly through, you don't need any communication, it communicates through actual power lines where the voltage changes a little bit, the frequency changes a little bit, the turbine starts spinning a little bit, there's more resistance to the water, etc., etc. And this has always been the case. But as we move forward, you kind of might want to drop that paradigm and tell people to charge their cars slower, or you have very primitive ways in economics where you can just have a nighttime rate, or you can develop a little bit further. You can have hourly rates of electricity, but one way or another, you actually just discounting people's electricity or paying them not to use it, right? It will still cost you money compared to what would the status quo be. So this is also a solution that still costs you some amount of money, right? And when you analyze all these, if you do nuclear, you can kind of just analyze one situation after another. You get a good proportion of what the size of the plant needs to be, etc., what the flexibility needs to be. For battery as well, you kind of look at the local history of what the weather has been, and you can kind of size how much power would you usually need to shift from solar to the winter, from the solar midday to the evening, etc. Overbuilding capacity, if you again looking at it locally, you can just look the fast rate of the weather. But there is one more thing you can do is you can move the power around. But in order to understand that, you need to know not just what the weather has been here in Cambridge, but also what it is in all the neighboring places whilst you're in Cambridge, right? And so this suddenly gets you into, you really need to understand the spatial correlations of the system, of the weather system, as they manifest themselves in this algorithm system, right? So in this previous example, in this case, you can look at the situation and then solve it, reduce the amount of coal that you need to burn by utilizing the system of high voltage transmission lines. That's quite extensive over Europe, although the capacity is still limited, and choose to move the power from places which they have a lot of wind, or a lot of solar, or any solar, and that's the solution to your problem, right? You might not need to employ any coal plants whatsoever. You just use the electricity from nearby. And so that's what I'm trying to look at. I've been trying to look at in my PhD. And so this is the context for the modeling that I do. Every time you do some modeling or renewable modeling or any modeling whatsoever, you really should dig into what's the context that you use it and how does it impose requirements or limitation on the detail, on the scope of your modeling, right? So I've already spoke about renewables. I look at transmission, so you need the spatial correlation to be there, right? You can't just state in the independent weather observations and then treat them as a distribution which is just independent of each other. They are fully dependent. I'm using as good of a model of the grid as a researcher can use, which is this open model of the European grid, which requires you to supply certain variables, right? So there is model renewables. You can do many different things. You can just look at some sort of downward solar. You can look at wind speed. You can use wind speed at different levels and construct like an actual like height profile of the wind, and from that you can be a bit more accurate. But at some level, you start losing accuracy to other aspects of your system. So when you use this kind of system, that imposes both requirements and certain variables that you need to supply, such as rain for the runoff in the rivers, but also doesn't, it tells you the maximum coarseness you should really worry about. For example, the system isn't perfect because it doesn't know exactly where each power station is connected to, and doesn't, so for the grid, you've got each node is some sort of place where you connect the distribution network to it and draw and supply power from distribution network, but those are kind of uncertain, right? If you only look at the map of the transmission grid, you don't know what this extent of distribution network is. So what you do in this site is you some sort of Voronoi closest kind of connection to what's the node that's closest and connect that area to it, which has some errors associated. So in order to be really accurate, you then have to spatially coarsen to average out some of these misconnections that you've made where a town is connected to a slightly different node. And that just fundamentally just limits the resolution that you care about. You don't really care about kilometer resolution for wind and solar. You just, at some point, tens of kilometers is okay. And then there's many machine learning techniques that are trying to be developed for predicting the grid. Because traditionally the grid is a power system, which is a network, which is a cyclic network. So there's a lot of problems in terms of predicting the flow on the grid because it's a non-linear thing, right? You can imagine if there is like a power flows, there's two connections between two places, the power flows to the bottom one, at some point it switches because of something to do with the bottom side of your graph, and switches completely to the top one, right? So it's a non-linear kind of switch. So you have to use optimization techniques, which are physics optimization techniques, which are very computation intensive. So people try to develop approximations using machine learning. For example, Mingguo Chen, who was presenting here more recently. And for some of these techniques, they have synthetic grids. They have grids which are kind of just toy models of some sort of size and complexity, and then you can employ your algorithms on them. And For them, what the approach is usually is just generate some uniform distribution across the sample of the input data. But for a system such as this, which is driven by renewables, the distribution is not uniform. There is a certain distribution given by the weather that you feeding in. So in order to draw from the distribution, you have to construct it. And in general, just the point is, when they train their models, they use 10,000 synthetic data points because they just can draw from uniform distribution, right? Whereas uniform across many different dimensions. Whereas in the case of real weather, you only have so many examples to look at, right? So I've talked about expired weather forecasts, so let me introduce what expired weather forecasts are. There's not a secret that ECMWF is one of the best forecasters of weather on the planet. It's a collaboration initiated tangentially by the European Union. It's not associated directly with the European Union, but it's a transnational, trans-European project, which then has a bunch of other member states joined in. They all pay their member fees, and then they're tasked to produce the forecast, and then they also sell the forecast to some other actors, businesses, etc. And so all of the national operators, Met Office, all of the national institutes of meteorology, French and German, etc., use these models of ECMWF to then target it to do some post-processing and better models to target into the specific region that they have. I'll be talking about, they've changed their forecast system a little bit recently, but for a long time, this would be their forecast system, where they would have a single high-resolution forecast at 9 kilometers, running up to 10 days. It tells you the kind of best guess of what the weather is going to be. But because of weather is chaotic, that means chaos, just by definition, is that any small uncertainty or any small difference in the input amplifies, even though it's completely deterministic, non-probabilistic, like quantum mechanics would be, it's a classical system. Any small perturbation amplifies and amplifies and amplifies until you cannot predict what's going to happen. So further down time. So traditionally, you know that you can only predict weather only up to about two weeks. So that's why their main ensemble, and the way you get around the chaos actually is use multiple different initiation and then see how they evolve and how much you're actually picking up this behavior of unpredictability. And so they've been using this ensemble member, so 51 different versions, slightly perturbed, and then they run the same model on top of them of slightly different parameters. Again, they perturb the parameters of the model a little bit as well, and they run it forward to see what the prediction. And normally they would be running it for 2 weeks, which is kind of the limit of accurate weather prediction. But twice weekly, they would be extending it to all the way to 7 weeks, because there is some larger structure that you can, given by the oceans typically, those have slightly longer time scales, that then influences the weather in some slightly predictable manner. And what's important is they've also developed ERA 5, which is a reanalysis, i.e. It's like a best fit across all space and time of what all the weather variables, just the kind of wind and solar would be. And that's what many people use in their analysis. And therefore, ERA 5 and ES Extended share the same fields, right? You've got the same kind of solar fields and radiation and soil moistures and all these kind of concentrations of things. They're all almost perfectly matched between those two systems. Now, so expired means that you've predicted the weather in the past using this ensemble model, but since then you've measured it and something happened, so the forecast is expired. And specifically, I'll focus on the ES Extended, which is a 7-week forecast at a coarse resolution. And now, why would you use them? So I spoke about it before, but just to recapitulate, so you've got, this is if you have an input space to your model, right? You have to put some variables of wind into your model. There is only a finite amount of spatial location that you look at, finite amount of variables, so you can kind of imagine every single input to your model lies in some high dimensional space. And what you could do is you could sample uniformly from from all this space between some min and max values, and then plug those values in. And this is of course silly, because if you have two neighboring grid cells, one of them ensemble will be 30 degrees, one of them minus 10 degrees, which never happens in real life, right? But if you actually treat your system like many people do, is, oh, well, we'll model the supply minus demand in Germany or in France, and you never look at what was the relationship between those two. What you're doing is you are sampling uniformly across this space, right? If you're looking at all the possible things that can happen in Germany and all the possible things that can happen in France, you are in some way matching winter in France, or not exactly, but cold periods in France to cold periods to hot periods in Germany, even though they should be somewhat correlated, right? And so in machine learning, you sometimes do this, and then if you just not careful and do the analysis of your renewable systems place by place, house by house, etc., this is what you end up doing. So what you're looking for is this kind of space of what's all the possible weather situations that just not that are physical in some way. It's also a probability distribution. It's not just like a subspace. And the problem is you don't really. And when you're looking at a system that's going to be operating 2030 onwards, this is the only thing you can do, right? You have to be probabilistic. You don't know what will happen. You don't know the fate of the weather. There's only one thing that will happen, but you don't actually know what it is. So you have to look at it probabilistically. So anything you do is an actual probabilistic thing. And the most common probabilistic thing is to just look at the past trace of the weather and use that to construct this this probability distribution of the future, right? So this is kind of the what would the system do in the what would a modern system do? Let's say a lot of renewables, a lot of transmission, if it was operating in the past, right? And this is how you try to predict the future. And the problem is, so if you kind of collapse this onto one dimension, you only care about the solar panel, about this building, that's actually quite enough, right? You can kind of imagine that trace, flattening it to one dimension gives you kind of a good histogram of what can happen, and that will give you good enough extremes, etc. But as soon as you start combining this place and the place far away, and you assume to be there's some independence between them, you start picking up this probabilistic factors, right? There's all these situations that can happen here and all the situations that can happen there. And that means and you start kind of building this high dimensional space, and suddenly the trace covers only a small portion of the space, and most, even the plausible things that could happen are not covered, are not represented in the weather record. So this is the kind of illustration. You're trying to estimate what the surface is from just this trace, and there's many different surfaces that could fit this trace. Just don't know. And so what the explainer forecasts allow you to do, they initiate it from this trace and they diverge because of the imprecision of the knowing of the initial conditions. But they all predict something which is plausible. They predict something which has been predicted by the best understanding of the weather as we have it and the best way to model it. And therefore they kind of predict futures that could have happened if maybe the wind speed was a little bit higher to begin with.
So the blue is actually what happened in the past, and the red ones are all the forecasts around it.
Exactly. And they always start from what is true, and then they diverge. And some of them, what you're trying to do is on the mean of the thing, or some sort of understanding of what can happen. But at some point, they just completely diverge and predict something which could happen, but didn't because the wind was just a little bit too slow, or this cloud has shifted north instead of south, right? And so this is what the ensemble forecast does, and it's initiated twice a week with the 15 different ensemble members. There is a little bit of and you can kind of see, it's a gift that's worth playing anyway. You can kind of see that this kind of allows you to estimate the surface much better than just a simple trace. There's a little bit of parallel to people using global climate models, right? Global climate models are dealing with the same problem of not knowing what's going to be in the future. And so they do it by having the best physical model of understanding of the systems that interact with each other. They have much bigger systems, ice, ocean, atmosphere, etc. And then they just, instead of any predictions of what will happen exactly, or any kind of direct trace that you're trying to do. They're just trying to look at the distributions, and so they resort to ensemble modeling as well. And people have been so this is, for example, a study that has looked at this and then used some climate models, and you can again accumulate, so you get 40 years or up to 80 years of the past record, and then you can accumulate many more years from the climate models. So ECF and HM is one of the climate models that you can have, put them into your model, and get many more situations that you can look at. And then there is an example on the right. If you have kind of extreme events, they are usually defined by a return period. So like 1 in 10 years is just a thing that happens only once in 10 years. And so you can look at them, and in year 5, you would only have 4 of these things. But if you get 2,000 years, 10,000 years, you have 1,000 of these events. And suddenly you can look at them in study them much more thoroughly. And you can, so generally, climate models are 2 cores. They look at some sort of larger scale processes, and people have been trying to downscale them. So Europe Cortex is one such initiative trying to get the best downscaled models, and Europe Cortex is the thing happening over, because you don't really need to downscale it globally. You usually care about specific things, specific places. So the Euro Cortex is one. But here you deal with this kind of problem on the distribution shift, right? So this is a really nice graph that I just found on the internet on the Victoria environmental governmental site. And you can kind of see this is what climate models do. They initiate them about 1850 or just like deep in the past, and then they run them, right? So they have the best guess of how chemicals and bio sort of coverage and land interact, and then the sun and the different systems, moisture interact together in the atmosphere, and oceans and the ice and land. And then they run that system from some random initiation, and they keep running it for like hundreds of years, not like the ensemble forecast, which is a start today, and then they run it forward. And then they keep running it for another 100 years past, and they add this specific CO2 forcing, which is what we're trying to study, right? The effect of climate change on the system. And so this is what they do. So they run all the ensembles, and what they're looking for, they have a historical run period and then get the forecast run period. And the historical is important because that validates how good their model is to begin with, right? If it predicts something which has been within the observation, so here the observation is the dark line in the middle, and your ensembles are kind of covering that spread, you know your model is good, and this is how you evaluate it, and then you can run it forward to the place where you don't know what's going to happen in terms of both emissions, and you have these kind of scenarios that you put in. And the problem is, okay, we are now, if you predict the system that like supposed to be acting in 2030 and onwards, right? So climate change by definition is a change of this distribution. So the idea that I showed you about this kind of surface that is there is the surface is actually changing as you go into the future. It's shifting warmer, etc. And we've already, if you look at the historical run, which is the majority of these global climate model simulations, that one is actually different to what we already have in 2020, right? We are now at 1 degree warming roughly. And so if you're looking at the future system, there's going to be even slightly warmer than this, even in the best scenario. And then if you plug into your GCM the most, the stronger, the most desperate scenarios, the RCP 8.5, kind of business as usual, you end up in a completely different system. So in all of your climate model ensemble runs, you only have a small area that fits into what you're trying to predict, right? So you would have to limit yourself to only, you can't use the historical things, you would want to limit yourself to only the 2030s. And that will suddenly reduce all the data you can use from the climate models. The other problem being they are just worse models than this forecast model that is just run in much higher resolution and much kind of more understanding of specifically the atmosphere and some of these fields. Yeah, so the way that some people get around it, like the kind of the real, they actually use the model themselves and run it themselves, right? So they actually run 100 ensembles. They know that the model is good enough, and then they run 100 ensembles or 2,000 ensembles between the decade to actually match that. But then you have to actually have the computing power to run your custom model. And so, yeah, you can use the thing that's already been calculated, right? And the good thing is ECMWF stored everything they've ever generated in their archive. So this is on offline tapes. If in their archive, offline tape is a magnetic kind of storage that is just not connected to any power most of the time. And to access the archive, you need to either pay the license, which allows you to access that, but you can also, as a researcher, you can contact a member state representative, it's Metafis for UK, and you can get access, get the credentials, and you can then start sending requests. But the request, because it's a tape archive, the request, you send the request through their kind of script, and you submit it, and then the next day, they start processing the request, because what the tape archive is, a robot has to come, pull out the tape, spin it, read it into its memory, and then crops whatever you want from it and send it to you, right? The tapes have terabytes and terabytes because they store all the variables globally. So if I only care about Europe and some of the variables, I crop part of it. But each of the forecasts is on a different tape, and so you have to wait in the queue for everybody's request to access. And so that limits the transfer rate that you can download this. So this is what I've been doing since, I think, the beginning of this year. And you can start accumulating this. The good thing is ECMWF, the reason that they have a license is they have a good prediction, so people pay to do that. And if they were giving data for free, then they wouldn't generate this income. But all of the past forecasts, that's kind of, they don't really care about it. They won't generate any more income from it. So it is under Creative Commons attribution license. So as long as you say it's from them, you can use it and publish it freely, share it with people, put it on flash drive, anything, right? So that's the kind of benefit of the system. Right, so let's look at what it actually is. And so, and it's all because of storage requirements, each of the forecasts itself, it would be like 2-3 terabytes. But you only care about Europe, which is a small part of the world, or some of the place where your grid is situated, and you only care about the most important variables for prediction. So these are the most important variables that most people use from BNR5 to model the electricity system. And yeah, so this is what I've been accumulating. So you've got 2-meter temperature, and so you got temperature for which is going to be more and more a driver of demand. So people will be heating their homes based on the temperature that's around, more and more so with heat pumps. So already about a large part of the system have fully electrified heating, France in particular because of the nuclear they have, but there is many more things. But like temperature correlates to, okay, yeah, so temperature is the main driver behind so demand, but also influences the efficiency of solar panels and similar factors. So figures in some of the models. Wind, you have 2 different wind speeds, and based on how tall your wind turbine is and how highly it's situated, you kind of want to use both of them to get some sort of sense of the curve wind speed. And you've got different solar and thermal radiation that's just coming on the surface. That's a function of both the angle of the sun, the season, and the clouds. And runoff is whatever is accumulated over a certain catchment to go into a certain river where you have a run-of-the-river electricity system, run-of-the-river power stations, or some kind of reservoirs and power stations like that. And yeah, solar temperature level allows you to model better the kind of ground for heat pumps and also the solar panels. Dew point temperature is just a different way to encode humidity together with the temperature. So this will allow you to, it's again predictor of decline. And surface pressure. I've done a lot of surface pressure because a lot of the large-scale meteorological phenomenon and people do kind of patterns of weather. They do use surface pressure because it's the smoothest field, as the most kind of least random, and is the most accurate at coarser scales. So a lot of people just look at spatial patterns of weather and define certain kind of modes of weather operation based on surface pressure. But yeah, here is again the data set from a single forecast, and this is just a single location of the three most important fields for predicting the electricity system. And so you've got temperature in the middle, the wind at the top, and there's a short wave radiation down, which is the main PV driver. And you can see that they start all together from a single point, and then they predict the same weather. So there's 5 of them all the way through, but then the 50 start from the kind of week 2 to week 6. And you can already see that in the 1 week prediction, for example, the temperature, there's 4 ensembles that tell it's mostly going to be above 0, but there's 1 ensemble that tells you it's going to be below 0, right? 1 week. And this is the kind of modal shifts that happen, and they happen more and more the further you go. And at some point you can look at the chaos of Vienna, of the wind, for example, that's just some traces go up and down independently of the other ones. And so you can kind of see this is an independent prediction of the weather. It's harder to see for the solar because it's kind of, this is a 6-hour resolution. And so it tells you either there has been clouds that day or there hasn't been. Sometimes these variations could be due to like local shifts, right? So the cloud goes a little bit north, a little bit south, the wind blows a little bit, like more like rainfall is typical in this unpredictability. This is saying that meteorologists know exactly what's going to happen, they just don't know when and where, because they just know exactly that the front will keep evolving, but they don't know at which point it's going to just deposit the rain. And so it's similar for winds, etc. But this is not just like a local variation, and that this wind that comes early is just here instead of being a little bit to to the south. You can look, this is the single trace for the specific location, but you can look if you average all the wind, or average all the wind over a certain country, so like a small scale, or over the whole region that I'm downloading data from, this is the wind, this is a 10-meter wind. And so you can see that the predictions are completely different on the whole of the continent, right? So 2 weeks to 4 weeks in the future, we can't be sure if the wind's going to be low or high over all of Europe, basically. So this is just the nature of the global weather system. But this actually benefits the approach that I'm having in terms of generating as much data as possible, because you can look at these 4 weeks and they're kind of independent. You can quantify that using variance. And so this is for the specific that I was showing you, the average variance all over the system and for different variables. And you can see that there is some specifics because of there is some predictability. There is some unpredictability 1 week in the future, but some predictability 2 weeks in the future. Once you go to about 4 weeks, the variance just stays the same. So it's the same variance that as unpredictable 6 weeks as there are 4 weeks. There's some seasonality to the radiation, which hasn't been subtracted here, but you can kind of average this specific case by looking at this for a month, and then you can kind of see all of these forecasts. The variance starts at 0, they're almost the same, and then the variance starts climbing. There's a bit of a shift because of I only have 5 ensemble numbers here and 50 here, but at some point the variance is just high. So you can use these 4 weeks as independent. And yeah, so this allows you to use 4 weeks per run twice a week with 51 ensemble members. And this particular system has been run since about 2010. So it's 12 years of data. So over they've generated about 5,000 years effectively of data. It's in these 2 4-week chunks, but it is this much different situation as comparison to the 40 or max 80 years in the weather record you can get. To understand the system better, they actually run also a companion where they use the same system that they have, the model, and then instead of initiating it today for the forecast, they initiated this date last year, previous year, and then the 20 years prior to kind of understand, and then they compare it to the actual trace that you had to understand exactly where should they be improving the model, etc. And so they only run about 11 ensemble members, but it's 20 times the initial conditions. And again, they run it alongside. They've only been running it since 2016, but this allows you to add another 10,000 years to your data set, and suddenly you have this much data. Right, so what are the caveats? So temporal resolution is generally the most limiting factor. If you really want, like, people, power engineers sometimes are looking at the ramping that they need to do, so how much they have to change the power from 10 minutes, 0 to 10 minutes, or half hourly. And this is something you can't do if you have this resolution of your data, unless, yeah, this is something you can't do unless you use some sort of other method that will interpolate the data for you. Era 5 is so popular because they just took a single model and then fitted it to every single data point that they had: satellite, weather balloons, weather stations, right? This is different because this is a permanently upgraded model. So 2015 model is different to 2016 model. Sometimes they're better at predicting something, and then they made a decision to be slightly worse at predicting that in order to be better at predicting something else. And so this is just an nature data set that this kind of limits somewhat, or like you can draw conclusions from a certain year as opposed to the other, but also allows you to, this kind of adds to the variance that you have. So it generally broadens the distribution instead of, so maybe your distribution will be broader than it really is, but like it really is not what the distribution is actually uncertain, right? There is no distribution, there is a single future trace that will happen. But so this will give you a kind of broadening of the distribution because you have different model cycles. And if you just take this without the details of which model it is, I don't think anybody could track in each individual models. You can maybe exclude certain years because they are worse than others, but this is as much as you can do. And traditionally, there's a record of the evaluation of these models, but they've always been measuring something slightly different than what you want to use this data set for, right? They look at the high skill, how skillful it is to predicting what actually will happen, which the worse the skill is for me, the kind of wider the spread of the situation is, the more they would perturb it, the better it would be for me, or for this kind of purpose. What I really care about is the kind of bias, the distribution shift, if there was some sort of, and there are biases, and sometimes because of the model cycle, sometimes they're like half a degree warmer all the time, then they change the model, they're always half a degree cooler, and so there is just biases that go back and forth, and this is what you have to kind of empirically evaluate. The other thing is this data set, I had some sort of, I think it's about 1 terabyte per 1,000 years of data. So this is about 10,000 terabyte, 10 terabyte data set, right? And this is it's quite hard to share with people. It's not impossible, but it's not as easy to just putting it in Zenodo with a couple of gigabytes. And then in addition to that, if you actually want to run your model across this data set, working with a multi-terabyte data set is, again, such a problem because your computer can only process at a certain speed. So this is where the high performance computing comes. So let's say I've generated this variance by applying a variance calculation on the previous traces across all of the space and time and all the ensemble members, right? And so this is a thing I can do to a single file. And then I can loop through the files and do it to every single file, right? So this is what it actually looks like if you have this, if you have the data set, so you get these kind of, you have these different initiations that start a few days after, is Monday and Thursday. And you can look at, for example, here, you can look and study the seasonality or the variance of the solar peak, which is just given that because of the magnitude of the solar is seasonal, so is the variance. And in order to do this, I had to run the system, load each file individually, and do this procedure on the Cambridge HPC. I managed to barely hit the 12, it was 11 hours, 57 minutes, and they had a 12-hour cutoff point, so this was very lucky. But so what you want to do, but they have many different, you can scale up on their systems massively. You load each file independently, each file is independent, each dataset is independent, each ensemble is kind of independent, although they're stored on the same file. And so what you want to do is process them in parallel. But if I have a laptop or if I have a computer's lab virtual machine, then I only have one kind of block of processors. And so I want to have both the single computer, single storage, and also the HPC procedures for people to use. And luckily, you can actually get around this with a trick where you have a Python script that loops through the files, and then that's what you would run on your computer. But you can distribute it by just supplying, instead of a list of files, a single file, and then you say the output, and using it as a Slurm arranger, which is a very efficient way of scheduling systems in parallel, and they can run whenever someone's not using a certain core, etc., on the HPC. But you have to prepare in advance what is called a staging. So staging is preparation of a dataset. You copy all of the things into, for example, the fast access memory, so that you can read it efficiently in parallel. And then the stage out in this case would be aggregating all the outputs that you get and deleting, cleaning all those fast storage things. So this is, for example, one parameter you have to do. One specific thing, right? So if you looking, you can do this in parallel. If you're looking for the mean of the temperature, you do mean of each individual files, and then you mean them together because it's a linear function. The same with the maximum, right? But for median, you can't do this. You can't just do median of medians. That's something different. So there are specific algorithms. So the median/percentile algorithm is you choose a pivot, and then you parallelize the calculation, how many values are below and above the pivot. Then you compare, then you add them all together at the aggregation step, and you figure out that there is 60% is above the pivot and 40% is below the pivot. And so if you're looking for a mean, you would discard low interval, you would look at the higher interval. If you're looking for 10 percentile, then you would discard the upper interval and keep looking at the lower interval, right? And so this is how you parallelize median percentiles, and there are similar algorithms for many different things. But actually, sometimes they're not as efficient, because this would mean generating a whole array of Slurm jobs at each of the steps of the way. And this is kind of like a binary tree, right? So you'd be aggregating. And this would just mean you have to read the data over and over and over and over, because you don't have it read like at the same time. So what you want to do is actually design the algorithms in the knowledge of the data set. And for example, here is a specific thing you can do with this data set is, this is a temperature. It only ranges from like -40 to 40. And so you can predetermine your histogram bins, give each task a task to compute the histogram, the kind of how many counts are in the histogram bin. And then you add them all together. And from this, you can read out the mean, the median, with a 1 degree precision, right? And then you can iterate on that if you need a higher precision. But this is, for example, something that you can do custom to this. And so this is just to finish off the parallel processing and finish my talk. But yeah, so thank you for listening.
Okay, we have time for questions.
Thank you for the talk. I wonder, do you think what is the most interesting or useful information you can get from the 10,000 years prediction for decision making?
So one of the things is extremes, right? It's this kind of fact that if you're looking at rare events, which drive most of the cost of your system, you only have a couple of them in the past, and they will not happen exactly the same way. So what you want to take is not like super rare, but like if you take the 1 in 10 year events, or 1 in 5 year, which is maybe 1 in 2 year, that kind of every 2 years you would have the most destructive, most costly event based on some metric that you define. You can go through your data set and select that. And if it's 1 in 10 year event, you've got 1,500 of them, right? Which is a distribution. Not all of them will probably be as likely to happen, but you have a distribution that you can look at and then choose to build your system. You find that 70% of them are of a certain style, and you can address 70% of them with a certain interjection, instead of just looking at how could you address that one shortage that you had 15 years ago, and then maybe that will never happen again. You're not sure if that specific one will happen again, right? So it's these kind of extremes, and any kind of multi-combination thing again, right? There is a combinatoric factor that you divide by every time you look at kind of a multi-point situation.
Yeah, another crazy thing in terms of risk, right? So you want to quantify risk. From snapshots book, for example. And so to quantify the risk, you want to look at distribution. So right now you can say what's the probability the temperature will go to 50 degrees. You don't know. It could be going 50 degrees. You don't. Whereas what Taylor is proposing is you take a distribution, if you find out 3 times in the next 10,000 years, it can be going in the next 10,000 years, forecast go to 50 degrees. That is the quantification of that risk, which you don't have otherwise. So I think that mindset of thinking about risk is possible using.
Yeah, this is a criticism in the book that advertised, Simon Sharp's book, where traditional science, they predict you the best guess what they have, the mean, but sometimes you want to just know the probability of something which you care about, which is how often your system will not have energy. And you can define threshold for what's the like how little, at which point even your batteries start failing, and then you can look at what's the chance of that, and then you judge if that's acceptable or not.
Is your goal to publish this separate, or just like the data set with some interesting findings, and then?
Yeah, so one goal is, because to accumulate data set, you have to be doing this for half a year. You download 3 forecasts a day, 1 reforecast a day, and you have to accumulate them slowly, because even if I just went to GCMWF, they wouldn't be able, if they give me exclusive access to their tape archive, they will still have to read everything and crop a tiny bit out of it, and it will take time. So the data set just being assembled, it's still terabytes, but actually if you look at a certain year, it's year of predictions, that's 200. Yeah, the year of prediction is about 200 gigabytes, so that's kind of shareable. And it already has many more, or you can look at winters only and people download subsets of data set. So yeah, you have to go through dedicated archives like the CDR archive for environmental data. And when they like publish, when you talk to meteorologists and tell them you have a 10 terabyte data set, they're like, oh yeah, that's good, it's not petabytes. And so there is a kind of some people are used to working and storing these kind of things and making them publicly accessible through some sort of API. But yeah, so the first step is to publish it as a, and then drawing the conclusions is.
Could you go to the variance, one of the variance graphs?
The middle one?
The previous one. I was just curious, which ones are the 2 that have the lowest variable constant?
Wind.
Yeah, it's soil temperature.
But this is normalized to like 1. Oh yeah, soil temperature is pretty stable, and you can predict it quite well because it's a slow, it's a function of the sun and temperature, but it's a slow responding system, right? So actually, if you look at here, they were surprised. This is only for the week 2 till 4, so it doesn't go from 0. But you can see that soil temperature is much wider because at the beginning is actually the variance is still low between the ensemble members, and only at the end is kind of very high, which just tells you that, yeah, you can still predict how cold or warm the soil will be 4 weeks in advance, better than you could do with how cold or warm the air will be.
Yeah, and what is the other one, the previous one? What is the orange thing?
Oh, yeah, the orange, it's a bit of a, that's actually an artifact because you can see that the variance of the red thing, the solar, is completely seasonal, right? Like in the winter you get no sun, so the variance is, you can predict much lower. So you have to kind of subtract, but actually all of them are kind of seasonal. But so this is just an artifact here, and if you were to subtract that, the cosine of the solar angle, you get a much closer curve than that. Yeah, so that's an artifact.
But it seems that the temperature is the one with the highest variance afterwards, right? The 2 meters.
This is normalized. They should all reach kind of 1. So it's so 1 is just the maximum variance in your data set at each location. So when you average them, it comes down a little bit below 1. So it's that kind of yeah, it's really hard to determine what exactly is the scale, right? Because when you get a variance, it's in the units squared of whatever you have. So if solar radiation is kilojoules, thousands of joules, it's a different. So you have to normalize them somehow. Yeah. I think the main draw point is the line stays steady as you go between week 2 and 4. And maybe slowly as we get a better prediction, even week 2 and 3 will be predictable and will be lower variance, but right now it's the same, right? Yeah.
Any questions from online? A couple of people there.
Hello, Kishaf. I've got a question. Can I ask Peter?
Yes, please.
Patrick. I'm Jacqueline. So my question is, you have been using this to look at the weather forecast, right? You're using those data forecasts, weather forecasts. Have you been considering how this can be put to use for forecasting air pollution? Like, because I mean, the weather and air pollution are closely related, and it seems like if you have such a big chunk of data, you could do the same thing for forecasting air pollution if you have the ground truth for the past decades or more, and that can actually be very helpful in understanding how weather is related or correlated with air pollution, because the wind, humidity, all these are affecting air pollution.
Yeah, so I'm pretty sure this approach can be generalized to some other problems with specific variables. The one thing is, this is forecasting, I would call the thing that you're actually trying to infer based on what's happening right now, what's going to happen in the future, right? And a lot of people try to do that in order to control, stock up, first of all, control the price of the electricity, and but that's kind of, people are trying to be better and better than this. This is when you go really far beyond the kind of, you operationally trying to plan something which will be active in 10, 15 years. And you just have no idea what you have, like, you have no idea what exactly the weather will be, and you have to just look at the probability distribution. So if you have a similar situation where you cannot know in 10, 15 years, and you could imagine having more accurate distribution of the weather, and if it's not extremely sensitive to small changes, this could be applied to maybe similar things. Depends how well we can model the drivers of the pollution, for example, right? If pollution is like a function of a street, interaction between a wind and a street, and a car or a highway, and it's just too small of a scale, you can't use these things because they will be coarse, and it's still 6 hourly. So some things that, this cannot be used to figure out the kind of predictability of ramping the up and down, how quickly the electricity system will change, etc., because it just doesn't have a temporal resolution. So if a similar kind of sensitivity is in a different system, it will work. But if in general it's about some sort of daily aggregates and hourly aggregates of temperature and, I don't know, humidity and wind, it could work in other systems.
Mm-hmm. Thank you. And you've got this data available. You've got this data available yourself, correct? The weather data is already downloaded.
Only for these variables and the kind of wider European extent.
Mm-hmm.
You have to use the same scripts that I use to generate data for a different grid or different area. Yeah.
Okay, thank you.
It's forecasted with global, right?
Yeah, but they forecast the kind of, if you look at this kind of, the 600 gigabytes is the whole kind of global coverage, all the variables, and then I extract 6 gigabytes for the reforecast from it, or a few gigabytes. So yeah, they have a global coverage. There are European things, so they are a little bit, the accuracy is determined by the stakeholders, which are most wider European, but also Americans buy data from them, no others, etc. So they do have a pretty good global coverage as well.
Okay, we are a bit past time, so let's stop here. Thank you very much, Peter. And we will resume next week. Thank you.
For the air pollution, I guess it will be useful for one.